Section 11.5, alternating series. Before I do the alternating series, let me recall quick things. The first one is that the absolute value of sine any function is less than or equal to 1. Means the graph of sine any function bounces between -1, 1, -1, 1. That's what this means. Same thing works for cosine. Cosine f of x, absolute value between -1 and 1. And the third one is the arctangent of f of x is always less than pi over 2. So the graph of arctangent goes between -1, negative pi over 2, and pi over 2. We're going to use them later on today in this section. Now we can introduce the definition of alternating series. So we say an alternating series is a series written in the form -1 to an n a n, okay, or it could be -1 to an n minus 1 a n, or it could be -1 to an n plus 1 a n. Let's say n starts at 1, n starts at 1 to infinity, n starts at 1 to infinity. So any series that has -1 to an n, -1 to n minus 1, or -1 to n plus 1 is called alternating series. Because if you list down the terms of the series, the signs of the terms will alternate: minus plus, or plus minus, plus minus. Now, if the alternating series, so if the series, let's do -1 to an n or n minus 1. It doesn't matter which one. If this one, for an positive, if this one satisfies two conditions. The first condition, that an plus 1 less than or equal to an. In other words, it's decreasing. And the limit of an as n approaches infinity is 0. Then the series we started with converges by alternating series test, and we're going to abbreviate it with AST. So note something about this test. This test is saying if these two conditions are met, that the series is decreasing and the limit of an as n approaches infinity is 0. If these two conditions are met, then we can say the series converges by the AST. It doesn't say anything about divergence. Doesn't mean like, oh, I found the limit of an and it's not 0, then it diverges. No. Okay, it doesn't mean this way. Or, oh, it's increasing. Or both failed, like no, it doesn't mean otherwise. So it only tells us it's inconclusive if one of these conditions at least fails to work. It tells us that this test is inconclusive. We have to find a different test or try another test. So let's look at an example. Again, the example is telling us test if this series converges or diverges. Let's say -1 to an n plus 1, n runs from 1 to infinity, times n over, let's say, 2n plus 1. So it's up to you to start finding the limit or checking if it's decreasing or not. So if I want to start finding the limit of n over 2n plus 1, that's our an here, as n goes to infinity. That gives us what? They have the same degree, so it's going to be 1/2. Oh, this is not 0. So the AST fails to work here. right? The AST fails to work. But what do you think about this? Like when we found the limit and it's not zero, that reminds us about what? The divergence test, right? The divergence test, just to recall, it says if you find the limit of an and the limit is what? Is not zero or does not exist, then the series what? Diverges. That's what we call the divergence test. So since the limit is not zero, then that given series that they give us, n over 2n plus 1, diverges, not by AST, remember, by the divergence test. And that's our goal, was to check if it converges or diverges. We're going to look at another example. We're going to check if this series converges or diverges. So first we're going to find the limit. The limit as n goes to infinity for an, which is the square root of n over n plus 1. This would go to infinity over infinity. So to calculate such a limit, we can use L'Hopital's rule. Assuming everyone can find the derivative for the square root of n, which is 1 over 2 square root of n, derivative of n plus 1 is 1. So this will go to 0. So one of the conditions is met. One of the conditions of AST is met. Also, we need to check if it's decreasing. You can find an and an plus 1, but it might be a little bit difficult to compare them. You can. But another thing we learned back in section 11.1, we could convert or change that into a function in x and then find f prime of that. So the derivative for this one, I'm going to assume everyone can do this. You get by the quotient rule, and simplifying this up, that's what we get when we simplify. Multiply top and bottom by 2 square root of x. Now, remember, n it corresponds to x, like they are correlated to each other. So every time I say n 1, 2, 3, 4, I mean x 1, 2, 3, 4. So if I plug in 1 for x, that gives me a negative value. If I plug in 2, it's still negative. 3, negative. 4 will make it 0, right, in the derivative. 5 will get me what? 4 minus 5. That's negative. 6 will be negative. 7, negative. So it will keep going on from 5 on to be negative. So we say this is less than 0 for x bigger than or equal to 5. So in this case, we call it, if you remember, eventually decreasing. It's like decreasing, but eventually decreasing. So notice what happened. The two conditions of AST are met, that the limit is 0 and the series is decreasing. So by the AST, the given series converges. The given series converges. Next example. So we're going to go over this one here. First, we find the limit of an, which is this one, as n approaches infinity. If you get infinity or infinity, you can do L'Hopital, right? You can do L'Hopital if you like, 1 over 2n as n approaches infinity. That tells me it's 0. So the first condition is met. Then you let y equals f of x, which is x over x squared plus 1, and you try to find the derivative for this. So f prime of x using quotient rule and calculating this, I got this one. So if I substitute x1, I get 0. x2, I got negative. 3, I still get negative. And the more I increase the x value, the negative is still there. So this one is less than 0 for x bigger than or equal to 2. So the two conditions are met, decreasing and the limit is 0. So the given series, negative 1 to an n over n squared plus 1, converges by AST. By AST. Let's look at a slightly different kind of example. Negative 1 to an n, natural log of n over n squared. N starts at 1 to infinity. For this one, we start by finding the limit as n goes to infinity of natural log of n over n squared. So this goes to infinity over infinity. How do we do this? We can do L'Hopital, derivative to the top over derivative to the bottom, which is the same as 1 over 2n squared. And as n goes to infinity, this goes to 0. So the limit is 0, which is good. And then we need to check if this is decreasing or not. So how do we check it? We write it as a function in x and find the derivative. So how do we find the derivative for this? Quotient rule. We do x squared times the derivative to the top minus derivative to the bottom times the top one over the denominator square, which simplifies into this over x to the fourth. We could now, because x is bigger than or equal to 1, we could divide by x top and bottom or factor x and simplify. That will turn it to look like this. 1 minus 2 ln of x over x cubed. Now the question is this less than 0? And if so, when is it less than 0? So how are we going to check if this is less than 0? So watch how we're going to work on this. People say, hey, can I plug in values for x? Yeah, you can plug in 1, 2, 3, but assume you have no calculator on the test. How are we going to handle this? You don't know what ln of 2 is. You don't know what ln of 3 is. So let's see how we do this without a calculator. So I'm going to write on the left side. I know the denominator will be always positive because x is 1, 2, 3, 4, right? I care about the top. So on the side, I'm going to take that and say, when is this going to be less than 0, if possible? And I'm going to solve the inequality. Subtract 1 on both sides. When is this be less than negative 1? Divide both sides by negative 2. That will make it positive 1/2, bigger than. And then you can do e both sides. So that would be x bigger than e to the 1/2. And what is e to the 1/2? Is the square root of e. So that tells me that derivative is going to be less than 0. Is going to be less than 0. So f prime of x is less than 0 when x is what? Bigger than the square root of e. So eventually decreasing, right? Eventually decreasing. And because it's eventually decreasing and the limit is 0, then the series converges by AST. How about a slightly different example? Test if this series, negative 1 to an n, cosine pi over n. Test if it converges or diverges. So the first thing is we try to find the limit of cosine pi over n, which is an, as n goes to infinity. So this is cosine pi over, let's say pi over infinity, which is 0. And cosine 0 is 1, which is what? It's not 0, right? So then we say it diverges by the divergence test. It diverges by the divergence test. So far, we have covered the following: divergence test. We covered the P series test or P test. We covered the geometric series test. We covered the p-test. We covered the integral test. We covered the comparison test. We covered the limit comparison test. We covered the alternating series test. And we abbreviate them with DT, p-test, GST. Actually, the p-test, these are the same. Integral test, IT, CT, LCT, and AST.